All right, here we go. Here's your notes on the universe. Happy snow day. All right, so we're going to talk about the universe today. I'm going to also encourage you to check out the YouTube that has our science department lip dub that goes to the Big Bang as well. All right, this is a American Museum of Natural History video of the known universe. This one's also linked to our YouTube channel, so if you want to go ahead and look there, I'm going to skip over that right now. What it does is it goes through all of the astronomical observations that we have and looking at all different kinds of data as well. This image right here, if we look at just visible light, this image was taken from a piece of the sky that we aimed Hubble at when Hubble first went up, and we said, so if you hold your finger at arm's length and you look at your pinky finger, your pinky nail, it was taken from a portion of the sky that size that we said, we don't think there's any objects out there. And that's the difference between standing at an earthbound perspective and a space perspective. When we took Hubble and said, take a picture of that area up out in space, Hubble could see these images. So you see all sorts of galaxies. I would encourage you to pause this movie right here and see if you can identify some elliptical, some spiral, and some irregular galaxies. There are three pretty obvious elliptical galaxies. There's one here, there's two here, and there's one here. Then there are some very obvious spirals here, and then some irregular galaxies probably here. This one, not sure if that's a spiral kind of viewed on edge or if that's an irregular galaxy. This little guy right here, that's probably a spiral. You can see that beautiful S shape. We have to remember that ones like this, these lined ones, those ones could be a spiral or an elliptical galaxy viewed on edge. It's only these handy dandy ones that gave us their front face that we can tell for sure. Alright, so Doppler effect and redshift is how we know, one of the ways we know about our universe, and we'll be playing with this in lab this week. First proposed by Edwin Hubble in 1929, he realized that dimmer galaxies are likely farther away, and he observed those dimmer galaxies have a redshift. Their color appeared redder, and this is because when a light source is moving away from the observer, the light waves get stretched out, so it appears redder than it is. This Doppler effect you probably know by listening to some sound. Like here's a train, and listen for the train horn as it goes. So you can hear that train as it goes past us, but I'm going to start it over and have you hear when it's coming toward us and when it's moving away, because that's going to be important as we start to look at light and understand how light works as well. Toward us, at us, and away. You can really hear as that changes tone as it moves away, and that's really important because light will do that same thing. So when we look at this middle object, if we saw this in lab, but we saw it a little bit differently, we saw these dark lines as bright and all the bright patches as black. So this is just kind of a reverse image. It's the difference between looking at light that's emitted or light that's absorbed. We were looking at emission spectrum, and that's just the opposite of this image here. This is an absorption spectrum. And so this object here is not moving. So on your notes, you'd want to circle that spot that's not moving. And then this one is an object that's moving away. You'll notice all these lines that should match up are kind of shifted over here towards this red end. And then these objects, this object down here, again has the lines that should match up, but these lines are all scooched over towards that blue or that purple end. And so this object would be coming toward us, and this object would be moving away. So if this was some element like those hydrogen tubes or that nitrogen tube that we looked at, if the object was moving away from us, it might look like this. If it was moving toward us, it might look like that. These are a couple of animations that we can look at as well. And so on this Doppler one, this is a UNL thing. And so what we would do here is we can go ahead and start some emissions. Hopefully you can see this on this YouTube, but what you see here are these lines coming out, and there's the observer. Up here you'll notice here's our waves, and here's what our observer would see. If I move the object toward the observer, what you start to notice is in the objects that we see that the observer sees get all squished, and then as I move the object away from the observer, they get all stretched out. But you see from that top bar that though that object is still giving off the same wavelength no matter what direction I send it, it depends on which way it's moving, what the observer gets to actually see. And so that will be in your links on Blackboard, or you can get it from this PowerPoint if you download that PowerPoint from Blackboard, and you can play with that as well. This other one that I have here for you, this one is a little bit slightly more challenging here in that you actually have to do view online free. But here we have a fire truck, and so if I get the fire truck moving, I'm going to move him forward, and we're going to turn on his siren. And it's kind of hard to see again. I'll make it go faster to make it more extreme. But what you notice is up here, look how close together these lines are. And look back here how far apart they are. So if this sound was coming toward us, this would be like that higher pitch sound on the train. This would be the lower pitch sound on the train. The odd part about this animation is if I make it go backwards, it's even more extreme and a little bit easier to see. I've never known a fire truck that needed to go backwards that fast, but you never know. Okay, so those are some animations about what that would look like. And if we just bring this fire truck to a stop, what we see is no matter what, those lines that are given off are always the same distance apart. It's as that fire truck starts to move that those lines start stacking up in the direction that it's moving, and they get stretched out in the direction that it's moving away. And we'll play with this also in large group this week, or in small group this week, sorry. And there's a spot here then for you to go ahead and draw one of those animations in your notes. So if you want to stop the movie here, that would be a good spot so you can stop and draw. All right, so Hubble then said, well, hey, I can make an inference about this data that I see, that these farther galaxies are redshift shifted. So now he also figured out that if it's moving away and the farther galaxies are even more redshifted, he could figure out speeds, just like we saw on that fire truck or on that other animation, that the faster I made that object go, the more extreme that effect was. So a larger Doppler effect means greater speeds, and a smaller Doppler effect means slower speeds. Well, what that meant for Hubble was that the farther galaxies are moving faster. And so Hubble's law, in a nutshell, states that the farther the galaxy is from us, the faster it's moving. And then we can make another inference, that our universe is expanding. And so our book gives an example, because we use that so often, as raisin bread dough rising, or you can think of like a chocolate chip cookie. You put this little ball of dough on the cookie sheet, and then those cookies spread, and those chocolate chips move farther away from each other. And so all galaxies do this. The exception to the rule are galaxies within the same galaxy cluster. So here we see that raisin bread kind of example. But what we've got is two raisins here that are 5 centimeters, and they move to 10 centimeters. And if you look, these two 10 centimeters go to 20. So in the same amount of time, this raisin only moves 5 centimeters away, but this raisin moves 10 centimeters away. So those farther galaxies get stretched more or move faster, depending on how you look at that. And if we imagine this is our galaxy, then we can see how all those galaxies are moving farther away from us. But then that always begs the question, are we the middle? Because this would be kind of our perspective, is that we are this middle raisin, and then we must be the middle if everybody's moving away from us, right? Well, if we just did a simple matrix of dots and called these galaxies, and we said, okay, well, let's just take that image and, you drag the corner and you make it bigger, right? Okay, so if we then say, well, which galaxy do we live in? Let's say we live here, okay? Now we take that image and we overlay it to the other one. We're not in the middle, but we see that the universe is expanding. So we see that the farther the galaxy is, the more it's moved. The closer the galaxy, the less it's moved. But what if that wasn't us? What if we were actually over here instead? What would that universe or that galaxy see? And they see the same thing. So it doesn't matter that every single galaxy has the same observation, that all the galaxies are moving farther away. We are not the center of the universe. Which if we go back in history to ancient astronomy, the church would have been very upset with us at that point, but the science and church have kind of divided themselves over that. All right, so Big Bang Theory. So this kind of, the implication of all these galaxies moving away is that they had to start somewhere, right? And so the idea is that we should be able to trace that backwards, and if our universe is expanding, it had to start somewhere. That's the Big Bang Theory, is that all the matter in the universe used to be in one hot, supermassive ball, and 13.7 billion years ago there was some type of expansion or explosion, and all the mass in the universe began expanding outward from that point. And the evidence we have that points to that are those redshifts, that Hubble's law. And the other thing we have is cosmic background radiation. So imagine yourself sitting in a classroom and somebody slams the door or slams their books down. Every head in that classroom would turn towards the noise. You'd be able to hear where that noise came from. But in cosmic background radiation, that's us kind of listening for the boom of that Big Bang. What we find is it's all around us, coming from equally in every direction. And so we are in the boom, we are in the explosion. And so we have that evidence as well that says we are in this expansion that is the Big Bang. Here's a quote from Neil deGrasse Tyson from the Super Bowl in the year 2014, and he said, if the gridiron were a timeline with Big Bang at one goal, then cavemen to now spins the thickness of a single turf blade at the other goal. Here is a movie of what the Big Bang might look like. It gives that flash of light, and there's some type of pause and then continued expansion. And you can just see kind of the grid work of the animation kind of in the background as it expands. So then that begs the question, well, what happens? There's a couple of options right now that science favors. There's the expansion forever. If the universe started as a big, hot, massive ball, will it expand and cool forever? Or is there some type of cyclical thing happening? Maybe gravity would take over and it would stop and reverse and collide back into that point and then, go again. And what proof do we have of either of these? Why these two options as the ending? If we look at the amount of mass that we can find in our universe, and we know mass is important because mass causes gravity. Mass points to our expansion option, and that's the option favored by current astronomy right now, is that our universe will continue to expand forever. How long is that? We don't know, until everything cools off down to absolute zero and is just nothing. Or the crunch is starting to become more prevalent because of this thing called dark matter. So here's that image again I showed you at the beginning of all those galaxies taken from one pinky fingernail held at arm's length against the dark nighttime sky. And so this is visible light. Now, I've already told you that we have lots of other kinds of information that comes in, X-rays and gamma rays and all sorts of different versions of information, and one of those is X-rays. And so if we look at the same image but we use X-rays, what we see is this purple amoeba-like, shape, and those are X-rays. And so what we see are X-rays coming off of all of these galaxies. And these X-rays are caused when gravity squeezes the gases in space. They give off X-rays, okay? And so it's kind of a measure of how much gravity is there. Well, if gravity is caused by mass, what we're finding is there's too much gravity squeezing. There's not enough mass there to cause that much squeezing to give off that much X-rays. And so we're like, where's all this gravity coming from? And if gravity is caused by mass, then there's mass that we can't see, which, you know, makes your brain throw a little bit of a temper tantrum. Well, so we call that dark matter, just because there's too much gravity for the amount of mass that we can see and understand. And so we call that dark matter. Well, dark matter then doesn't give off light, visible light or energy like that, and we can only infer that it's there by the X-rays. And if we start to measure how much gravity based on those X-rays, we think there's as much as 10 times the amount of dark matter as visible mass in galaxy clusters, and enough that it would make up about a quarter of our universe. And it's found as this halo around those galaxy clusters. So then, you know, how do you explain the expansion part? They give that extra expansion that's by those more distant galaxies dark energy. You're not going to be quizzed over dark energy because that's that whole acceleration. We're not really sure. Just know that this dark matter stuff is why we're thinking that big crunch is possible. So then, if we look at those X-ray images a little bit more, and we look at dark matter, what we find then is if we start to look at these galaxy clusters. So this is a galaxy cluster, and we start to look at that and we say, okay, well, what do galaxy clusters look like when they're put together? Here's a good spot to stop and just look. So you might want to pause the video and just look at this. And I would ask you, what does it remind you of? It reminds me of like tissue. So just like, I don't know, like not even muscle tissue, but like maybe smooth muscle. I don't know. I don't even know. It looks like tissues, but to me. But if you look at that, that's that X-ray, and you start to look at how all of those galaxy clusters start to become connected. It's almost like there's this fabric of galaxies and dark matter throughout our universe, and it, you know, you think of us as so small, but it really makes you feel like you're part of something bigger, you know? A little science humor. Hubble constant is very nearly scientifically proven. They need one more trial of the Large Hadron Collider to prove it. It was started to be published as of last spring, and hopefully they'll get another run-in and be able to prove it. They found the Hubble constant, and by figuring out where some subatomic particles were not. It's funny how I've always said you can define something by defining what it's not, and that is how they found what they're calling the God particle, which is part of studying our universe. Is you have to get down to molecular level. And subatomic particles. It's kind of cool. This is another video about the Large Hadron Collider. I will also put this on your Astronomy Universe playlist that is on my YouTube channel if you want to check it out. It's kind of fun about looking at what exactly is the Large Hadron Collider and how they study our universes at that subatomic particle level. One of the big fears about the Large Hadron Collider at first was the possibility of creating a black hole inside of it, and then what would happen? Turns out those subatomic black holes actually evaporate quite quickly, and they're not dangerous at all. Okay, so this week in lab you will be looking at that. We're finishing our measuring the universe. Hopefully the snow day won't mess us up too bad. All right, have a great snow day, guys.